Good evening, everyone. Okay, tonight we're going to be, our presentation is going to be the ABCs of LSST and GMT at the RFCML, which is the ABCs of the Large Synoptic Survey Telescope and Giant Magellan Telescope at the Richard F. Karras Mirror Lab. Okay, so speaker tonight's Dean Ketelsen. The making of large telescope mirrors has continued to evolve through the 20th century and is culminating in the activities of a couple of different groups with distinctly different styles. In this talk, Dean will talk about the methods of the Richard F. Karras Mirror Lab, formerly the Stewart Observatory Mirror Lab at the University of Arizona. Focus will be on two distinctly different telescopes, the LSST, now the Vera Rubin telescope, and the GMT. Lab's efforts have revolved around making large substrates of 8.4 meters diameter, nearly 28 feet. He will discuss why the Mirror Lab has stayed with this method of fabrication and show why these telescopes are some of the most difficult large mirrors ever made. In addition, he hopes to reveal a surprise that almost anyone interested in astronomy will be excited about. Dean Ketelsen is a Midwest native, former Iowa farm boy. He developed an interest in astronomy, attending a one-room country schoolhouse, and obtained an undergraduate degree in astronomy and physics at the University of Iowa. Thanks to a work-study job in the astronomy department there, Kitt Peak National Observatory came calling, and he has been in Arizona for 40-plus years, switching to optics after taking an optical shop practices class at the Optical Sciences Center at the University of Arizona. He has worked on or supervised a crew making 4 3.5 meter mirrors, 6 6.5 meter mirrors, and 6 8.4 meter mirrors. Since 2008, he retired to St. Charles, Illinois, but still works part-time at the lab as he splits time between the two locations. Now mostly a master optician emeritus, his job title still remains technical expert. Please welcome Dean Ketelsen.
Testing, can you hear me?
No. Let's try it again.
Can you hear me now?
Yes. Sure.
Well, I don't know if I want to hold this too, but I was told to bring refreshments, so did you all bring something to pass around? This is a piece of glass that we cast into our mirrors. It's kind of cool. E6 from Japan. We've only made one mirror from Corning, from Pyrex, and it didn't work out for us. This is Japanese Pyrex. I'm going to pass it around. It works out to about 80 bucks a kilo. So I'd like to have it back, but if not, if you want to pay me 80 bucks a kilo, you can probably. So yes, I work at the Mirror Lab. It's tucked under the football stadium, University of Iowa. I wish. I went to University of Iowa. Go Hawkeyes. Under the football stadium, University of Arizona in Tucson. I split my time almost 50-50 now between Tucson and St. Charles. And when I'm in Tucson, I do work part-time at the University of Arizona still. They still let me in the door. My job title is officially technical expert. It's kind of a made-up job title, but there you go. Anyway, tucked under the stadium. See if this works. Yes, here we go. Back in the 80s, the Booster Club for the Wildcats wanted to build a pavilion for donors and people to donate money. So they wanted to build what's called the Wildcat Club, this facility up here. And Roger Angel at that time was looking for a place to put a high bay area to cast mirrors. So that formed a partnership. So the Mirror Lab is this bottom structure, and the Wildcat Club is up above for game time. There's a TP that sticks through the Wildcat Club, which you'll see what is that's about in a minute. This is the high bay area. We have 2 machines, the large polishing machine and a large generator, and between them is a test tower that poked up between up into the Wildcat Club. This has 2 heads. You can put a polisher on each. They don't generally work at the same time, but we have done that once or twice. Otherwise, it's a high bay area. There's, you'll notice there's no high capacity overhead cranes. We use an air cart, which you'll see demonstrated a little bit later. The mirrors weigh typically 20 tons, and in their cells, about 40 tons. So it is kind of a pain to move these big things around, but you'll see how we do that in a few minutes. Back in the old days, this is one of the large binocular telescope mirrors, which was, you know, we broke our teeth as we went along. We started with the 3.5 meter mirrors, 6.5. This was at 8.4. The LBT, LBT, 8.4 meters, f1.14. So they were pretty aspheric, very steeply curved, about 18 inches deep in the center. So if you had to walk on the mirror, and you had to polish the, when you started a polishing run, you had to walk on the mirror. You'll see why in a minute. When the surface was soapy and slippery and you had to walk to the center, it was downright dangerous. And you can't imagine how slippery a polished mirror is when you're out there scrubbing the polishing tool. Anyway, life was simple back then. This shows, with the null lens up here, this is a blow-up of it. You have to make your primary mirror look like a spherical mirror to the interferometer. And it used what's called an Offner doublet, and that transformed the aspheric curve for the interferometer up on top, made it look like a sphere. This is our metrology person, Mike. He's a tall fellow, 1.96 meters for scale, and you can see the hexapod for positioning, the null lens, the vibration insensitive interferometer up on top, and he's holding here a hologram which sits at the paraxial focus of the mirror, and both tells you if the null lens is properly spaced out. Sort of, we wanted, you know, Hubble. We were developing this mirror lab during the times of the Hubble issues. In fact, it was my boss that went to Perkin-Elmer to analyze what went wrong and found the spacing error. So we for every null lens that we had a hologram that when inserted in place would diffract the right orders back to the interferometer and tell you that the spacing was correct. It worked out very well. It also determines the paraxial focus of the primary mirrors. So we actually use a mechanical tape calibrated by NIST to measure the focal length of the mirrors that way. We get it down to a couple tenths of a millimeter using a mechanical measuring tape. Here we are, we're out on the mirror. We have to wash off the lap because we can't really move the lap off the mirror. So we're out there on a wet soapy mirror scrubbing the lap. We don't have a clean room. It's an industrial area. It's pretty clean, but certainly not a clean room by any case. And then you scrub the mirror, and then you start the polishing run with a clean lap and mirror. We use pitch typically. We sometimes face it with polyurethane polishing tools. We don't use bare pitch much anymore, but we use the artificial polishing polisher surface polyurethane typically.
Did you guys make the laps as well?
I'm sorry?
Did you make the lap yourself?
We made everything, pretty much. That complicated polishing tool, we'll talk about that in a few minutes. How sensitive is the interferometer? My friend Jennifer and her husband came by when I was testing once, and I helped her up on, I made her take her shoes off, but I got her to lay on the mirror for a count to 100, and then she climbed off and did a metrology run, and you can easily see her outline from her body heat making the Pyrex expand. So it's pretty sensitive, and it fades. It does fade for a while. If this were in the telescope, first of all, it wouldn't see a thermal bump like that, and we actually actively air conditioned the lab by blowing, I think, 4 liters per second, a huge amount, into each core to actively control the mirror temperature during the night of observing. Jump to 12 years ago, life gets a little harder. We finished both of those LBT mirrors successfully. The LBT is a spectacular telescope. I think I've got a picture of it later on that you'll see. This is Leslie. I use her for scale because she's like 4'11", so make our mirrors look bigger. And it always, you know, I get used to optics doing weird things occasionally, but I still can't understand why a reflection in a curved surface gives you an erect image. It's always confused me. Usually you get anyway, you should see the feet on top, right? If it was a flat mirror. Anyway, we were doing the LSST mirror here. You can see the sign there, and you can see the ultra steep curve on that. We'll get to that in a second. LSST, the Large Synoptic Survey Telescope, now called the Vera Rubin Telescope. It's an amazing beast. I'm happy to have been part of it. But it's designed to cover, just like back in the old days, like even before our time, they had the 48-inch Schmidt and the 200-inch Palomar. One was to give you the wide field view of the sky with the Schmidt plate. The Schmidt cameras had a 6 or 8 degree field of view. Then the Palomar could zoom in on things that it found. Sort of the same with this. It's a 3-element telescope. The primary 8.4 meters in diameter, reflecting up to a 3.5 meter secondary mirror, which makes the light almost parallel back to a third mirror up through a pair of correctors to a 3.5 degree field of view that's 65 centimeters in diameter. It's pretty huge field of view for an 8.4 meter telescope. For scale, these are 0.6 arc seconds. The 10 micron pixels, I believe, sample something close to 0.2 arc seconds. I'm not exactly sure. But across the entire field of view, the images are well under half an arc second. Well under. There are also filters in there for whatever wavelength you can work. When the bright moon is out, they can go to redward wavelengths to minimize the moonlight effects. It's a pretty amazing system. This is Suzanne Jacobi holding the 65 centimeter scale replica of what the focal plane would look like, and that's a proper size image of the moon. So like I say, a huge field of view. I mean, a lot of people, if any of you go out and do photography with a wide field telescope, I mean, the moon is considered a large field of view, where this is many times the field of view of the moon. 3 gigabytes per exposure, approximately estimated to be 30 terabytes per night. One of the statistics I heard, the director of LSST came and talked to our astronomy club in Tucson one night, and they're planning on running the data. It's somehow getting from the Andes to Rio de Janeiro, and they're going to stuff the data into a fiber coming out up in Louisiana somewhere, and running it what the maximum rate they can send down through an optical fiber. The data at the beginning of the night works fine, but by the end of the night, they're like 6 hours delayed because they can't push data through an optical fiber fast enough, which seems amazing to me. Anyway, this is a drawing of the mirror. We cast these mirrors, we spin cast them, right? Well, there's no way to spin cast a double curve, so we spun it for the outer curve, and as a result, the glass in the middle was about 10 to 12 inches thick, so we had to generate that out. So that was the first step of the process when we started the front. We have a big honking diamond wheel that we throw lots of mist at. You can see the little pellets there. This is a coarse diamond pellet, about 30 microns, or 30 microgrid, 30 mesh diamonds. So they're about 1 millimeter or so across. When the diamonds get dull, they pull out and leave leave an empty socket where the diamond sat, and as the bond material wears away, it exposes fresh diamonds. We can take glass off up to about a cubic centimeter per second, a few cubic inches per minute. Finer diamonds give you a smoother finish and less subsurface damage. Here's near the beginning of generating the M3 curve. This is towards the end. The black line on the outside was the goal. It's about 5 meters in diameter of the 8.4 meter surface. 5 weeks of generating 2 cubic meters, 5 tons of glass, 27 barrels of swarf to be removed. We had a centrifugal filter to take the glass powder out of the coolant to make it work more efficiently. And then once you know it, we finished the generating, we finished the beveling and edging, we were literally done with the generating process, and we broke the mirror. It was all hidden behind that ventilation system because of the mist. It has the silicon dust in it. You can't inhale that, so we had a ventilation system. The spindle, in this case, it didn't have a wheel on it of any sort, and it was moved out without being high enough because this thing is literally like 24 inches deep in the center. It was moved out and punctured a hole in the inch-thick faceplate. We can fix that, and we did. First of all, we stop drilled. There's 3 holes here that we stop drilled the fractures that were live fractures. We removed the loose glass. There was a big gouge here that we took all the fractures out that we could. Fractures we wicked UV curing cement into so that to make sure that they wouldn't grow any. And we made a dummy. Well, that's my boss, but we made a duplicate area in practice on repairing that before we did the real thing. And I developed, pretty much whatever I could figure out to fix it is what we did. You know, again, you had to write reports and make sure everything approved. But we, the stop drill holes, we had little glass balls made. We had a glass ball grinder and polisher. We would lap those into place like here, and then we would mark how deep they had to be and cut them off with a diamond saw. Put a nice little bevel on it. This is one we glued in. And similarly with the big one, we had a generator we used over at Optical Sciences. Lapped that into the divot and cut it off at the right thickness and wick glue into it. Wait a few hours for the glue to wick in before you turn on a UV light and glue it into place. And it's pretty much a perfect match. And I ground and polished this 12-inch diameter sample, and you couldn't hardly tell. You could see a little bit in the bond line, but outside of that, more than a ½ millimeter away, you couldn't see any hint of it. We made the hole big enough that we took out one of the stop drill holes, so we only had 2 stop drill holes to repair. And so it was on the actual mirror. This is the actual mirror. You can still see some of the original generator marks. But once the mirror was processed, you can faintly see the 2 plugs that we put in, and then the outline of the large one. This is, once the mirror was polished, I went back and took a picture of it, and I used a test plate on it as well. And you can't, other than a little bit of a turned down edge right at the bond line, you can't really see it. And we never saw it on the interferogram, so it's a successful repair. The stress lap that we use for this mirror, this is how we've done pretty much all of our mirrors that are rotationally symmetric. We have 18 actuators that have a servo motor that turn a ball screw, which push on a 7-to-1 lever, which tighten these bands across the mirror so that the 2-inch thick aluminum, aircraft aluminum plate can be warped to take on the ideal shape of wherever it is on the mirror. So if you imagine, if you're out on the edge of a parabola, say, this thing can warp this aluminum plate the couple hundred microns that you would need to conform to the theoretical shape of that off-axis parabola, wherever it is. And it worked great for doing all of our rotationally symmetric mirrors, including the LSST. Here it is polishing the or loose abrasive lapping on the M1 surface. The M3 surface is already polished, I believe, at this point. But yeah, wherever it moves, it takes on the off-axis shape of that surface area. It works great. You can spin it, you can move it in radius, and it has a lookup table that tells it if we're at this rotation, if the lap's at this rotation and this radial position, we must have this tension on the bands, and it worked out great. We measured with a laser tractor system, a little corner cube. Measures the surface. That works great. We measure the ultrasonic thickness of the faceplate. That has to be no wedge. We can't have wedge in the faceplate from center to edge. Lots of things to worry about when you're making these lightweight mirrors. There's the polishing of the M3. This was 8-9 years ago. Hard to believe. Time flies. We have predictions of what a particular stroke will do. There's some polyurethane polishing pads. You can slap those right on your grinding tools and get a shiny surface for optical testing. It worked great. This is the M1 surface, the outer ring, 19 nanometers RMS, about 1/3 of a wave RMS. And then, the thing I forgot to mention, the first drawings of the LSST, the two curvatures, people were going to make two different mirrors. Going to have an M3 mirror and an M1 mirror, and they were going to be separate, independent pieces of glass. We said, hey, we can do that as a single piece of glass, never have to worry about aligning those two mirrors. So that's what we did. So this way, we have to align the optical axes precisely, and also you can't bend out the shape of one to fix the shape without affecting the other one. So this is what we ended up with, 19 nanometers and 18 nanometers RMS for the two surfaces. So it was, you know, a good initiation for what was to come. This was harder than the LBT and other rotation symmetric mirrors, but it was still easier than what's coming up. People ask, well, what's the spec on the mirror? Well, it's a complicated spec. It's a structure function spec. Depending on the separation, if you look at 2 points on the mirror, if those 2 points are 1 meter across, they can be up to 120 nanometers difference in height. If you're looking at separations down in the inch range, they have to be better than 20 nanometers. They have to be a very smooth surface at higher spatial frequencies. You know, at the edge of a 8.4 meter mirror, they can be a quarter wave. We don't care. But you want it to be smooth at higher spatial frequencies. This dotted line is the spec curve, and the M1 curve was this blue line. So once it gets below the spec line, we don't say, hey, we can do it better. We say we're done. So current state of the LSST, they finished installing the final parts of the mechanicals in March of this year. They have a dummy mirror installed. The mirror is there, it's in the cell, it's been aluminized, and they're working on the telescope and the drive system and all that stuff. As for the camera, this is one of the mosaic of the array of the camera. I forgot what the date this was, but this picture was, I saw this picture about a year ago. This is the first scientific picture from the actual camera. They took a pinhole projection of a Romanesque cauliflower head. That was the first picture of the entire array of the camera. And as I understand, first test at the telescope should happen about a year from now. So they should be integrating that, and I'm guessing first exposure should be coming out in a year or two. giant Magellan telescope, a project from hell. Nothing is ever easy. No one wants symmetric mirrors anymore. What they wanted 7 mirrors working together, all of them 8.4 meters in diameter. The easy one should be the center one. We haven't done that one yet. We're doing the hard ones first. And each of those primaries has its own adaptive optic secondary. I include this picture because you rarely see semi-tractors used for scale. Anyway. The test tower dominates the center part of our lab, and you can see one of the methods for testing is this long black thing. You'll see a diagram of what that does in just a second. It's called the scanning pentaprism test. If Hubble had this, we wouldn't have had if Hubble had done some of these things, we wouldn't have had a Hubble incident. So it would have been perfect the first time. The test for GMT and the prior state of the art. The LBT that I said was looking back, it was pretty easy. It had about 1.4 millimeters of aspheric departure. The GMT, 14 millimeters of aspheric departure, so 10 times the asphere. And unlike this one, which is at least rotationally symmetric, this one has no axis of symmetry. When you take an off-axis parabola and you treat it like it's on axis, it doesn't have, it has an axis of symmetry. The radial line across it has an axis of symmetry, but it doesn't have a rotational axis of symmetry. So it's not easy to polish well, as we found out. We can't get to the center of curvature anyway, but we have, you'll see here in just a second. What we did, we modified our test tower, and we put a fold sphere here. Any of you that have Newtonians with a secondary mirror that might have a little power, what you get at the focal plane is astigmatism. And so you can counteract some of the astigmatism by having a fold sphere out here. And then we have a second fold sphere, and then a computer-generated hologram. So between the two fold spheres and the hologram, we can correct that almost 15 millimeters of aspheric departure. The fold sphere up here, it has an interferometer test. You can actually monitor the figure of this mirror while you're doing the fold sphere. And there's another hologram here that measures the position of the smaller fold sphere. So there's a huge increase in complexity of the testing to get a test done. So you have 14 mil. That's what the figure looks like of the mirror. 14 millimeters of departure. After the first bounce off the first fold sphere, it's reduced to 6.1 millimeters. And after bouncing off the second fold sphere, 320 microns, which is fixed by the holographic optical element before going into the interferometer. And of course, from the interferometer, it goes through the fold spheres and holographic optical element twice, one bounce off of the primary. So I forgot, someone said that there's like 19 surfaces that we have to worry about the alignment of, non-trivial. This is my face and reflected in the big fold sphere on top of the test tower. I like that. I feel like the Wizard of Oz. You know, I am the great. I am the great and powerful Oz. I'm looking down from the top of the test tower, and really, what I am, I'm just happen to be at the center of curvature of that mirror. Kind of cool. I have fun. There's 4 independent tests. There's the principal test that I just described, put an interferometer looking through the 2 fold spheres and the holographic optical element. And you can also do a Scott's slope test. I'll talk about that in just a second. It's a, well, I'll talk about it in a second. The other test is a scanning pentaprism. It's that black arm that you saw a few slides back. If you imagine this off-axis parabola is in the telescope, if you tilt things now so that this black arm is now making incoming starlight. and it bounces to where the focal plane of the telescope will be. We actually have a CCD up at the focal point of these off-axis parabolas, and when you scan a laser source across the surface, any movement you see in the focal plane is because there's a little bit of a slope error in the primary mirror. So you can track some of the aberrations of the mirror with the scanning Pentaprism test. It's only mostly sensitive to low-order aberrations, astigmatism, focus, the low-order stuff. Because we're subtracting a lot of the low-order stuff from these tests, that helps you determine, makes the tests more complete by combining the high-order stuff with the interferometer, low-order stuff of the scanning Pentaprism test. And the laser tracker, you just have the laser tracker up here measuring the surface directly with a little retroreflector. And that's also the low-order test. So these 4 tests have to agree to make sure there's no Hubble effect going on.
Question?
Scott's test, I like to think of it as kind of a scanning Ronchi test. Anyone does Ronchi testing? Yes, sir.
Sorry. So you need the off-axis parabola because you have multiple mirrors all focusing on the same point?
Correct. There's 6 mirrors around a central one. All 6 of those have to be off-axis parabolas.
Okay, sorry.
This Ronchi pattern is mounted up after the second full sphere, and there's a camera next to it that records the reflection, and so they can use that to measure the surface also, like a Ronchi test, slope test. You can integrate the shape or slope errors. You can integrate the slope errors and get a height map of the mirror. That's how it works. Comparing the principal test and Scott's, they agree very well. Difference is very small. Both of them, you ignore the low-order polynomials that you can back out with the other tests. Stress lap did not work for these off-axis parabolas. They're not rotationally symmetric where they excel. So we had to go to dwell-control smaller tools. Now this works very well too. However, you'll see in a second, it's hard to follow the change in A-sphere around the mirror. We'll get to that in just a second. Yes, we walk on nearly finished mirrors. We have to, the imaging of the different tests change, and so we have to put fiducials down to be able to map out how the distortion effects of the imaging affect the phase map, the hit map. So we have to do a lot of fiducializing to measure. We want to be able to hit the right spot. We want to be sure to hit that high, and if we don't know exactly where that high is, how are you going to make it lower? So we need to measure the distortion of the optics in the imaging systems. Here's with them all in place. How aspheric is it? This is the same mirror, the same GMT mirror. It's the one we're working on now, GMT3. We've finished 2 of them. This is GMT3 that we're actively working on now. This is the side of the mirror towards the vertex. It's very nearly spherical. Again, same test plate. This is the side away from the vertex. There's about 30 waves of astigmatism there. So any tool that you have, you need to be able to either follow or let it conform to the surface that you're polishing. It's extremely tough mirror to figure. The first 2 mirrors, we managed to do it with small tools down to 2 or 3 inches. This one we've gone down to as little as 1 inch, 30 millimeters. And the result of going to small mirrors is that you get a choppy surface. And you can see here, you can see some of these should be smooth fringes, and they're not because the small tools are sort of chopping up the surface. Everyone has ever made a mirror around here knows that small tools will give you a rougher surface typically. But we can do a few tricks, at least some low order stuff. This is a final measurement of GMT1, and you say, wow, that looks really crappy. Well, we're allowed to rotate it and shift it slightly, a couple millimeters in the cell, so we can shift it and rotate it slightly. And then we could end up with, this is a theoretical, I believe, this is a fit. And when you subtract you can bend out astigmatism really easily. And with only 16 newtons of force, which is pretty small, you can effectively bend out, this is the astigmatic error, and you get down to less than 30 nanometers. So by shifting, clocking, and a little bending, and again, this has adaptive support. So there's 164 actuators, so you can easily bend out errors like this. This is the first one, 19 nanometers. Second one was finished a couple years ago. Depending on how many forces you use, you can get it down to 14 nanometers with 15 newtons of force. So we're having trouble with this one. You know, people are always coming and going too. I mean, I'm mostly gone, not that I'm responsible for much of anything anymore, but I help out when I can. But it's always a challenge, it really is. Let's see. You have a mouse there? Yeah. I'm going to probably zip through this a little bit faster. Does the mouse work from over here, I wonder?
It's
Let's
Bluetooth.
give it a try.
Sure.
This is our orbital polisher. You can see the mirror speed up and slow down as it goes over highs and lows.
So the mirror is moving?
The mirror, this is a time lapse effectively. So yeah, when the mirror is spinning and the lap is slowly spiraling, like 1 inch per rotation, but you don't really see that part. You're just seeing the mirror speed up and slow down.
Now, is that speed change predetermined, or is it adaptively doing it?
It knows where the highs and lows are, so it knows where it's speeding up and slowing down.
Okay.
Yeah, it doesn't have the range to come over here, unfortunately, the mouse. Now the run is done. Note the time. The time is 3:20.
Wherever that screen is.
You'll see how long it takes to wash off a mirror. The problem of some of these mirrors is that we're only allowed a 2.5 inch hole to drain, and when you have a mirror that big, because of Coriolis forces, the water washes down and it misses the hole. And so it takes a long time to scrub the mirror down. Seems like we're scrubbing all day. Scrub the mirror to start, scrub it at the end of the run. It's already 3:40 there, so we're 15 minutes into the washing cycle.
Is that just water, or are there other agents?
Yeah, that's just deionized water.
Now, are they washing to change grit, or are they?
We're going to move it over for a test, an optical test.
For testing.
25 minutes in, we got the squeegee out. Thing to note, look at the reflection. You're actually seeing the aspheric surface. If it were rotationally symmetric, you wouldn't see that wobble in the reflection.
Is there a reason that at 8.4 meter is that, I mean, I know that's the size of the lab, but is there Is that the biggest mirror you can truck across the country, or?
It's the biggest mirror we can make because we'd have to expand the crane supports in the casting lab to get anything bigger. Effectively rebuild the building. The plan was always to make a 7.5 meter mirror, and then Gemini was 8.1, and then the Subaru mirror was 8.2. So Roger needed to have it bigger than 8.2. We need to put 8.4. So there's the A-sphere visible in the reflection of the spinning mirror, which is kind of cool that you can see that. So the air cart, which you'll see here, there's an inner frame that has jack screws to pick it up, and then there's air pads under the corners to move the mirror out. It takes literally one person can do it in a few minutes. And then we hook up the circulators. These are fans that blow air past the back plate of the mirror through the cell to help the mirror equilibrate overnight, and then we test it the next morning. Current status of the GMT mirrors. This is an artist conception because they closed, they shut down in March of last year for COVID, and they were shut down through the end of the year. 33 weeks they were closed. I think, as I understand it, I didn't see any current information really, but they've got a skeleton crew working on the water and power distribution lines. The building has not been started, but somewhere on their website I saw that they're hoping to open the telescope with 3 or 4 mirrors in 2026. So that's the status of the GMT at the moment. We're the third mirror, we finished 2 of them. The third mirror, we're down to like 40 to 50 nanometers RMS. We need to make a factor of 2 improvement, and we're having some issues seeing the whole mirror and getting the edges done. If you wanted an 8-meter mirror, we could have finished it 8 months ago, literally. But it's that the outside 4 to 8 inches, that's just so tough. Casting. I talk about casting because this last spring I was asked to help with some of the publicity shots. So all these pictures you'll see coming up here I took myself with my equipment, except for one of them. But the mold starts with a hearth plate of hard refractories. There's close to 1,700 cores, hexagonal cores in these mirrors. So each of those cores has a hard refractory base plate, and the hole in here, each core is held down by a silicon carbide bolt. Here, Randy is they're waiting to modify one of these to get the right spacing to do the tub wall. The hard refractories are the only parts of the mirror that are recycled. The cores are softer refractories, and they are destroyed when they're washed out of the solid mirror at the end of the process. Inconel bands, heat-resistant steel wrap around the tub walls to keep things together. They expand 10 inches from room temperature to 1,200 degrees C. So they're terminated in these air cylinders, and they're fed by dry nitrogen on board the spinning part of the oven, so that they're designed to the same force is applied as they move 5 inches from room temperature to full heat. Oven walls are up, insulation installed around the Inconel bands. The band seat firing minimizes shifting of the refractories and bands in the casting process. So you can see the resistive heater elements and the thermocouple sticking through. Full heat pulls 1.4 megawatts for any of our operations. CNC machining some of the odd shapes at the end of the mold installation. It's really fun to watch. It takes about 10 minutes per core. does, you know, CNCs are always fun to watch anyhow. They do tool changes and different operations. This is in a dust collection system. The refractories, aluminum silicate is really bad for your lung, silicosis. So it's all done with a dust collection system in an enclosed space. Here John is taken off a finished core that's just been machined. Of course, if these pictures were taken these days, he'd be wearing a mask for COVID as well. You'll see in the videos coming up that everyone is masked. We were shut down for about 4 weeks last March, but then we realized that we really had to open up to maintain a schedule. So the people that could work remotely did so. The people in the lab to run the machines maintain proper distancing, different doorways, cleanliness that are still being followed now. But we were able to get a lot of work done in the last year. Starting from the center, cores are fastened down to that hearth plate down below. The caps are glued on last. You can see Damon here is gluing on the covers. You need to have the outer one done to pin these cores next to the ones that are going to be installed here. But once that second row is there, you can put the covers on those. Another pre-fire cycle to set the mold, and then you have to inspect that for anything that broke loose during the pre-fire process. And here, I'm too far to start the movie again. I got a number of
or over to the side, so it's on the screen. Now you can click on.
yeah, there's a couple of these movies coming up, so. Yeah, why don't you just move the cursor over the picture and start it. I like how fast they work in time lapses.
How long does the comb build
I'm sorry?
take? How long does the comb build take?
Does
From
what
start to
take?
finish? How long does the laying down this part of it?
Oh, the mold production takes about 3 months, and the casting takes about 3 months, and the mold clean out takes about 3 months. They can cast 1 mirror per year, but we can't polish them that fast, so they would start stacking up. Oh, I just figured out how to start it by hitting the button the second time. Okay, meanwhile, while they're inspecting the mold, the glass arrives. We had 3 semis of glass in storage. We usually buy the glass about a mirror ahead of time. And we had 3 truckloads of glass come in, about 20 tons, all nicely packed from Ohio to the U.S. Of course, when they're big chunks that are already broken out, they make it about a ton at a time in a big clay pot. And they've already broken it to make the chunks for us, so we don't have to worry a lot about breaking it again. Here we are unboxing it. This is, they inspected the 20 tons in about 2 days. You'll see the whole process here in this segment. Wrapped very nicely in peanuts. We got lots of Japanese peanuts. We'll be unpacking them from the peanuts.
This is exactly what you passed around.
I'm sorry?
This is exactly what you passed around.
Yeah. This fellow is blowing off the dust into a dust collection outlet. You don't need to clean the glass. It's pretty clean. Just get the particulates off of it before it goes into the mold. Randy does an amazing job. He sorts every piece of glass. There's a polarizing filter down here, and he's got polarizing glasses. So under cross Polaroids, he is judging the good glass from the mediocre glass. And he sorts the pieces. I don't know if you noticed, but there's two grades. There's the best stuff is the low seed, low stress glass, and that's going to be put in the mold last. They'll form the faceplate. The high seed is the lower quality, and they'll get put in the mold first, and that'll form the backplate and the rib structure of the glass. Yeah, he looks at each piece. He rotates it, looking for impurities. What's he looking for? There's a seed here that has high stress associated with it, and there's a whole area here that has stress associated from the stress birefringence revealed by the cross Polaroids. They used to, some of this stuff they would just reject out of hand, and then there used to be a guy that could cleave little pieces, cleave this piece out of it. You know, with a rock hammer and a torch, you can start a fracture and cleave that out. But now it's just put in the backplate, and we don't really care a whole lot about it. Okay, this is a few days later. Again, 2 days to sort the glass. This is a long work day. You probably can't see it. It's 5:10 in the morning there when they start. These guys work 10-hour days. They work 4 days a week, but they work 5 a.m. typically. They get off at 2 o'clock. So here's the first pieces of glass in the mold. And again, I like the time lapse. I think this was 2 or 3 frames. I'm sorry, a frame every 2 or 3 seconds. But they're humping. They're doing this stretching and stuff for 20 tons of glass. So they must be sore at the end of the day. This is what it looks like normal speed. After seeing it in time lapse, it's like, oh, can you guys go faster? But then you got to realize too, all this glass is sorted ahead of time. It's about 50 pounds per box rolled up onto the conveyor belts, and there's guys, this has all been sorted, so this is all the low quality glass that's going to be part of the backplate, because it's going to run into these little centimeter wide cracks there. When the glass melts, it's going to run down to form the backplate and the ribs, and whatever glass is on top later on will stay up in the faceplate.
Does it take a couple days for them to cover that?
No. One shift.
One shift.
One
Wow.
shift, 20 tons.
Wow.
That should be really strong.
3 guys is all it's doing?
Well, and the guy's feeding them. You'll see them in a second too. I really like this one, focusing on the chunks. And again, I'm writing along on the oven as they spin it, so it looks like the chunks aren't moving, but the people are.
Does there have to be like a specific density? Is that why they're placing them so specifically?
No, they're good point though. The soft refractories are indeed quite soft, and if you carelessly drop one in there, the sharp edge of the glass can make a mark on what will be the back of the faceplate, or you could break off stuff that would contaminate the mold. So you want to put at least the first layer down pretty gently. So that was the the stuff, the boxes from down below are being fed up by a different crew. There's like 8 or 10 people that are helping out during sorting and mold. I think this is 2 or 3 seconds per frame as well. Fisheye lens, so and then this is just the top layer of good glass. It's hard to judge exactly where it should be. So, and it flows some as it rotates. It flows in and out a little bit. It all evens out depending on your rotation rate. But I let the camera right along with the oven, and then I save it before it gets knocked over by the scaffold that they're on.
Right on the outside, you have more work.
Final 3 chunks. Each have a chunk in their hand. These are the last 3. Damon gets the honor of dropping the last one in. And the mirror was only uncovered for like 5 minutes. It was pretty quick. These guys are a team that have worked together for a dozen of these mirrors mostly, and they know what job is coming up next. Before you know it, the scaffolding is gone, and they're getting ready to move the top of the oven down. Rich Wortley is the new head. The Randy, the guy on the left that was placing glass blocks, officially retired, but he's training Rich for a mirror or 2 before he makes himself scarce and retires to his wine closet. Here is installing the oven lid. Last step of a long shift. Well, I didn't point out when they dropped that last chunk in, it was straight up 1 o'clock. So from 5 a.m. till 1 o'clock in the afternoon, they placed 20 tons of glass. And this is still that same day. It sat here for a couple of minutes, and I was able to take some still pictures that you'll see in a second. And that's it for the day. Here's the last peek I took. A couple still shots looking at the glass before it gets transformed. Temperature profile from room temperature, 0 degrees centigrade, effectively. They have a brief hold at 500 to make sure, if they go beyond that point, the glass starts melting together, which is bad if you need to change something. So they bring it up there, and they have like a 8-hour hold. And if all goes well, then they continue to go up. I think they can go up at about 25 degrees per hour is a centigrade, the max they can go. 1265 is the maximum, and they hold that for 12 hours. Then they cool it just as rapidly, and then it's the anneal time for about a month and a half, 0.1 degrees per hour, so about 2.5 centigrade per day through the annealing process, and then a more rapid cool down to room temperature. It takes about 3 months altogether for the entire casting process once the glass is installed. Randy pointed out to me there's a little port here that you can look through, and when the mirror's spinning at 8 RPM, you can't jump on it. But before it jumped full rotation, I actually looked through it and took a few pictures, and you can see the glowing heater elements and faintly see the glass. The only light inside was the red light of all the heater elements, so it's kind of washed out. but it was kind of cool to see. This was not full speed yet. It took about an hour and a half to ramp up, and I wasn't going to wait around for an hour and a half to get the full speed. But one rotation was about 8 seconds at full speed, about almost 8 RPM. And this is the most amazing video I've seen. I reduced it just to look across the mold of the far side. I won't bore you with the wide-angle views, but this is the most exciting part. As the temperature rises, the glass just looks like lumps of jello, forms a layer about 5 or 6 inches deep, and as it continues to get more fluid, it drops into the mold very quickly. There's bubbles at the surface that come up and pop, and you want glass about 2 inches deep at the edge, or at the end when the glass fully runs into the mold. So, and that's what you have. This was, that casting was in March 7th, just before my last trip up here in the spring. And then I came back for the summer. And when I got back on August 1st, they had just unwrapped that mirror, and that's what it looks like out of the tub walls. And right now, that mirror was just moved to hang vertically, and they're cleaning up the mold material. Probably not even as we speak, but these days, that's what they're working on right now. This is the center mirror, the GMT4. It has a center hole. But the same thing, they have a spider with 36 annular supports that they fasten with RTV, a 2-part RTV, but otherwise it's the same silicone support you use, silicone caulk you use for bathtub caulk. And it supports it during the mold clean out, and for fabrication of the backplate. The spider actually holds the mirror when you grind and polish the back of the mirror. And then they use high pressure water to remove the mold material. The soft refractories come off with high pressure water. You can pick at it with your fingernail or a screwdriver, but high pressure water is safer. And then you're left with a hollow piece of glass that, if placed carefully back down on water, would actually float. It's only it's about 80% lightweighted, so if you put it on a body of water and put an outboard motor on it, you could have a little portable island. You could get it down to Chile that way by putting a motorboat on it and push it down. These are just a couple things in passing. This is old technology. This is probably 8 or 10 years old now. But one of the things that we did at Stewart, we built a secondary mirror for the Large Binocular Telescope that is 1.5 millimeters thick. It's precisely a spheric, 1.5 millimeters thick. It's got 670 magnetic magnets glued to the back of it, and they interface with little voice coils up here, and they can shift, put forces on that mirror to do atmospheric corrections using the Gregorian secondary mirror. This is an example. This is without correction. It's a blob of a star. With the correction, they can separate 0.16 arc seconds. That actually transforms to a triple star system. And I think this is my last picture. This is one of my favorite instruments because I photographed this from Safford, about 12 miles away. I actually have a time lapse somewhere. But each mirror, they send up a beam. Each of these is actually closely spaced, 3 laser beams surrounding the field, and they can similarly get improvement in the scene by a factor of 2 or 3. So the intensity is improved by a factor of 4 or 9. You know, that's a couple magnitudes of gain from for a 8.4 meter telescope. So pretty cool. Anyway, that's it. I'm sure you don't have any questions for me.
Well, Jack and I were down there in January of 2014 we toured the Stewart lab at the time, and the LSST was in final grinding, and they had 2 large Magellan mirrors in the back. So what's the whole timeline to finish that LSST mirror from the time you start till it's done?
The LSST went pretty quickly. The hard part was, I think we were slowed down a couple of months for repairing the hole we punched in it. You know, it's getting to the point where I can't even remember what year that was. I have to look at the slide that had the year. I usually identify my pictures by year, month, and day. But I think it was like a couple of years to do both of those surfaces. You know, it's rare that you get to finish the optics before the telescope's done. And in that case, I think we delivered the telescope 4 or 5 years before they even started building the telescope. It's been in storage somewhere. Oh, I mentioned in my talk description of a surprise. Well, I can't talk about it yet. But it involves a new space telescope that, you know, some of you might have heard about the decadal survey that's coming out about where to put money for what telescope projects. And one of our engineers is involved in this secret project that I can't talk about yet. And I said, Steve, it's not listed on this decadal survey list of options. And he gave me a Star Wars analogy saying, we are the rebels on this distant planet and no one knows about us yet. But it involves Elon Musk, I hear, and there will be a space telescope being announced shortly this fall that will shock everyone. So that's all I can say. Yes, sir.
How is the Magellan telescope different from the multiple mirror telescope that used to be on Mount Hopkins?
It's very similar, except a generation or 2 later. The MMT, for those of you in the know, Aidan Meinel, who was director of Stewart Observatory back in the 60s, got 6 lightweight Air Force quartz honeycomb mirrors and put them together into a multiple mirror telescope. And they worked out all the bugs to get those to combine to form a single image. And it worked reasonably well. The 6 72-inch mirrors, about as tall, big as diameter as I am tall, equivalent to about a 4.5-meter telescope. But they had the opportunity to replace it with a single 6.5-meter mirror and triple the light gathering power. So about 20 years ago, they replaced it with a single 6.5. They still call it the MMT, and really, it's got a primary and a secondary. That's multiple mirrors, right? Those mirrors are still available if anyone wants a 72-inch mirror at f2.8. The off-axis parabolas that we're making make it a different game, though. When I think they predominantly did the steering on those with the secondary mirrors, as I recall. But now it's just part of an enlarged pupil. It's equivalent to a 25-meter telescope f.7, which is what the GMT will be because of the off-axis parabolas. You don't have to work so much to align them. It's all part of the phasing that they're going to have in the support system. I don't know a lot of the details. I just do the optics. Yes, sir.
Short question and a longer question. What's the melting point of the glass?
It's about the same as your Pyrex cookware. If you raise them to 800 degrees centigrade, they'll start to get soft.
Okay, so it's around 800.
800 C, yeah.
Okay. And the second question is are there more than one oven? You showed us an oven that you're making the GMT mirrors in. Do you have other ovens lying around?
We have what's called the meter cubed. It's the space for doing test pieces. It's literally a meter deep, meter wide, meter tall for doing test pieces. But no, otherwise it's just, we started off with, you know, it doesn't take much to make an oven. Some bricks and heater elements and You know, Roger Angel started with something in his garage, electrical resistance heating, gas heat. You know, it's like a kiln that potters use. You can, if you can control the temperature well enough, you can melt and anneal wine bottles and make yourself a telescope mirror, right? But the Mirror Lab has gone through 3 revisions. Back in the 80s, when I was a new hire at Optical Sciences, Roger had a oven at the basement of Optical Sciences that was capable of doing a 1.8 meter without spinning. And he did a 30-inch mirror that the Astronomy Club now has in Tucson. They haven't done anything with it, but it is a couple of 6-inch mirrors without spinning. Then they made a 2-meter spinning oven, and then they went to the Mirror Lab, did the 3.5s, the 6.5s. Now the 8.4s are the biggest they can do.
Is there anybody else who makes this level of glass besides O'Hara?
O'Hara, I don't know how to answer that because I'm not sure what their current capabilities are, but Zeiss, of course, made the glass for the European 8.1 meter telescopes. They do a different tact in that you can't melt zero door or ULE, the Corning zero coefficient of expansion material, ULE or zero door. They don't get really liquid like Pyrex does. The best that zero door can do is they can slump it over a mold, heat it up, and they can put a curvature into it to save the generating costs. I don't know, since the European ESO was finished, what, about 10, 12, 15 years ago, I'm not sure, there aren't that many customers for 8-meter mirrors. And the market's sort of been cornered by the Mirror Lab. If you know, Pyrex is okay. If you can tolerate the low expansion materials, you know, we'll make it for you at pretty reasonable cost. Going to zero expansion material is more costly for the material. Their mirrors, the 8.1 meter mirrors of the ESO, they're only 6 inches thick. You know, when we melt our Pyrex, when it first melts, it's about 6 inches thick also. But the fact that we have the ribs and a backplate, our mirrors are much stiffer because they're like an I-beam. They resist bending. We can get by, we have 160 actuators that we can support the mirror and actually bend the astigmatism a little bit. I think they're required to have many more actuators because being that it's 8 meters and only 6 inches thick, it's very much more flexible. So there's advantages to both mirrors. You know, Roger used to buy us, you know, our mirrors are stiffer, more resistant to wind loads. You can drive the temperature, you can blow temperature controlled air into the cores and control the mirror substrate temperature during the night. You can actually track it during the night. If you have a solid piece of glass 6 inches thick, you can't really, the thermal time constant is much too long, but it's zero coefficient of expansion. So, you know, you have mirror seeing, you have seeing effects from if you have a mirror that's 5 degrees warmer than the air, you get a boundary layer on the surface that affects your images. So you want the mirror at the same as the air temperature. We can drive our mirrors at that temperature. The thicker mirror, the 6-inch mirrors, you know, you can't do that as well. So there's advantages of both. So anyway, what was the question?
Last question, really. Annealing, do you guys do anything to promote it, or does it just do a natural annealing?
Oh, we have to do our annealing when we cool the mirror down. It's all part of that 3-month process. We can, you know, Palomar took, what, 13 months to cool down when they cast Palomar. That's because the glass was much thicker. You get stress buildup when you cool it down quickly if it's got considerable glass thickness. The thickest part of our mirror is only a couple inches thick. You know, it's got the mold material. Otherwise, as far as the glass goes, it's really only maybe 2 inches thick. So we can finish our annealing in that month and a half of the 3-month process of the casting process.
And so it just naturally cools, and
Yeah.
you don't have to do any
No.
introduction of like cold air or whatever.
Nope. Ooh, I ran long. Sorry, guys.
Thank you very much.